This resource is the fifth in a 5-part series on vectors. Part 1 defines vectors. The component form for a position vector is presented with an example. We also discover how to find the magnitude of a vector. Part 2 considers basic operations with vectors. We look at adding and subtracting vectors in component form with examples. We also consider scalar multiplication of vectors. Part 3 considers writing the vector in terms of its magnitude and direction. Part 4 describes how to find the resultant force when two different forces act on the same object. Part 5 looks at the dot product of two vectors, looking at multiple examples, including a word problem. In an earlier resource, we considered scalar multiplication of vectors, in which we multiplied a scalar quantity by a vector. There is also a method for quote-unquote multiplying two vectors, called the dot product. While scalar multiplication resulted with a vector answer, the dot product yields a scalar quantity for an answer. How does the dot product work? Suppose we have two vectors, v and w, written as position vectors. To find the dot product, we multiply the x direction components and add that to the product of the y direction components. Let's look at some examples. Suppose we have the two vectors v and w, where v equals 5i plus 2j and w equals 3i minus 4j. What would be the dot product of vectors v and w? To find the dot product, we multiply the coefficients for I and j and add those products. We will multiply 5 and 3 and add that to the product of 2 and negative 4. Our dot product will be 15 minus 8. So the dot product of vectors v and w is the scalar quantity 7. Let's see another example. Suppose this time v equals 7i minus 4j and w equals 2i minus j. We want to find the dot product of v and w. Plug into the formula for dot product. Doing the multiplications, we have 14 plus 4. Our dot product is 18. We can also use the dot product in real-world situations. Suppose we have the vector v equal to 260i plus 300j, which represents the number of gallons of regular and premium gas sold at a particular station. Another vector w equal to 2.50i plus 2.65j represents the cost per gallon of regular and premium gas. We want to find and interpret the dot product of vectors v and w. Plug into the formula. Multiply. So v dot w equals 1,445. But what exactly does this number mean? This amount is really the amount of money that the gas station made selling regular and premium gas. There is an alternate method for finding the dot product if we know the magnitudes and direction angles of the two vectors, instead of their position vector notation. We need to find the angle between the two vectors. If we call this angle theta, then the dot product of vectors v and w equals the magnitude of vector v times the magnitude of vector w times the cosine of theta. Suppose the magnitude of v is 10 with a direction angle of 25 degrees, while the magnitude of w is 15 with a direction angle of 70 degrees. Find the dot product of v and w to the nearest hundredth. First, we have to find the angle between the two vectors. We subtract their direction angles to get a theta of 45 degrees. Plug into the formula. Doing the operations, we find that the dot product is 106.07 when rounded to the nearest hundredth. In the physical world, the dot product of two forces is known as work. As we saw in the previous resources, forces tend to be described in terms of their magnitude and direction. As such, the geometric version of the dot product is more useful for finding work. Suppose a force of 80 pounds is used to pull a box up a ramp inclined at 10 degrees from the horizontal. The force is exerted on a rope that forms an angle of 33 degrees with the horizontal. We want to find how much work is done pulling the box 25 feet along the ramp. We use the geometric formula for the dot product. Plug in the information we know. Note that we have to find the difference between the angle of the incline and the angle at which the force is exerted. Completing the calculations, we found that we have used 1,841 foot-pounds of work.